Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to learn how to establish hypotheses. Most business research starts off with a research hypothesis, so let's talk about that first. A research hypothesis is a statement about what the researcher believes will be the outcome of an experiment or a study. For example, many business people may believe that selling soft drinks in a store at eye level will create greater sales. Other people believe that the prime interest rate is inversely related to the bond market or the value of bonds. That is, as the prime interest rate increases, the value of the bonds decrease. And still other people believe that workers who commute further to work have a higher incidence or rate of absenteeism. We have many research hypotheses that are available to us and that we consider, but in order to actually test a research hypothesis, we have to convert it into a statistical hypothesis. Let's learn how to formulate statistical hypotheses. Statistical hypotheses come in two parts. There is the null hypothesis, written as H sub 0, and there is the alternative hypothesis, written as H sub A. When we transform our research hypotheses into statistical hypotheses, the result is that we have two hypotheses that are mutually exclusive. That is, there is no overlap. You have one or you have the other, and they are collectively exhaustive, which means that between the two cases, it includes all possibilities. The null hypothesis means null, or comes from the word null, meaning, in a sense, nothing. And what this means is there is nothing new, or we have the status quo, or if you will, the old theory. So nothing new is occurring, nothing new is happening. The alternative hypothesis, on the other hand, has the new theory or a change in the status quo. As an example of setting up statistical hypotheses, suppose we have a research hypothesis that a soft drink company is underfilling bottles that are supposed to have 20 ounces in them. If we were to discover, for example, that one bottle contains 19.9 ounces, do we have enough evidence to prove that the company is underfilling bottles? Well, even if we went to court, probably the case would be thrown out, because it's unreasonable to expect in a manufacturing environment that all bottles will have exactly 20 ounces in them. So we have to be reasonable in our expectation. So probably a more reasonable hypothesis would be that the company has an average of 20 ounces in the bottles. That is, all bottles won't have 20 ounces, but they should average 20 ounces if the bottles are labeled with 20 ounces on them. So how do we begin to write statistical hypotheses to demonstrate or test that the company is underfilling these 20-ounce bottles? Well, our alternative hypothesis would be that the mean is less than 20. Quite often in statistical hypothesis testing, we put what we are trying to prove or our new theory or our new idea in the alternative hypothesis, and oddly enough, we start with that. If our alternative hypothesis is that the company is underfilling the bottles with 20 ounces, then the null hypothesis, because we have collectively exhaustive, mutually exclusive hypotheses, would be that the mean is greater than or equal to 20 ounces. These become our statistical hypotheses that we're going to test. So let's look at them one more time. The hypotheses are mutually exclusive. There's no overlap. Together, they contain all possibilities. The alternative hypothesis, in this particular case, supports the research hypothesis that we're trying to test. The null hypothesis, then, is that the company is either actually putting 20 ounces in the bottles on average, or they're perhaps even overfilling the bottles. It is often standard methodology to write the null hypothesis with just an equal in it. That is, all null hypotheses have an equal sign. Now that may seem a little odd since we want these to be collectively exhaustive. You might wonder what happened to the greater than sign. The theory or the idea is that if we reject a null hypothesis because we have a mean less than 20 ounces, then we're also rejecting the greater than case. And so we don't include that in statistical hypotheses. One rule in statistical hypothesis testing that's very important to remember is that we always assume that the null hypothesis is true when we begin the test. So in our bottling problem, we assume that the bottling company is doing the correct thing, that the machines are in adjustment and they're averaging at least 20 ounces in the bottles. The alternative is they are underfilling the bottles. Suppose that we go out and we randomly sample 50 bottles and we take them to the lab and we test them, and the result is a sample mean of 19.99 ounces. Should we reject the null hypothesis based on this sample mean? Well, let's think back on our central limit theorem and how sample means are distributed. So suppose our sample mean falls below 20 ounces. We have a dilemma. Are the machines actually set to produce 20 ounces and are actually doing that? Or is something else going on here that we need to pick up and understand? We're using our sample mean as an indicator of it. Understanding the sample means are normally distributed and that we may get some sample means down here by chance, we have to make a decision. At some point, we draw a line in the sand, if you will. We'll call that the critical value. And once we do that, we have made the determination that any sample mean that falls, in this case, below the critical value or outside the critical value, if you're on the upper tail or lower tail, is going to be in what we call the rejection region, because the sample mean is so far away from a hypothesized value that we no longer believe that the null is true. The rest of the distribution in this case is called the fail to reject region. So in all statistical hypothesis testing situations, we gather sample data, we examine the data, and in this case, if we're testing a mean, if our sample mean falls below the critical value, we will be in the rejection region, and we will make the decision to reject the null hypothesis. If our mean does not fall in this region, then we will make the decision that we are going to fail to reject the null hypothesis.